Okay, so we're going to look at a couple examples in this video dealing with RL circuits and RC circuits. Now we're going to first start off with a very simple one here, where it's just literally an R and an L circuit here, and then we are given that the initial energy in the inductor is 0.960 joules, and then we're asked to find an expression for the current in the circuit. So we're asked to find this current here. Okay, so how do we go about doing this? Well, the first thing we really want to do is just remember the formula for this current from the previous lesson, which is I0 e to the negative t over tau. So there's really just two things we need to find here. We need to find I0 and tau. So I just need to find I0 and tau. And then once I find I0 and tau, well, I'll be done. And one of these is very easy to find. Tau is actually the easiest one to find first. Not that I is going to be difficult, but we know that we have a formula for tau, which is just L over R. And this would be 120 millihenries divided by 2 kiloohms, which gives us 60 microseconds for the time constant. Now in the previous video I said I was going to explain how do I remember that it's L over R versus R over L. Well, remember that we said that time constants have to be small. And if I forgot the formula, let's just say, or didn't look at my notes and I did R over L instead, well, I should just, by doing this, I should know that my answer doesn't really make sense, because I get 2 kiloohms divided by 0.120, because that's 120 millihenries, and you wind up with 16,667 seconds. As a single time constant, that makes no sense, because we said, okay, it takes about 4 or 5 time constants for something to charge up or discharge. And so what we're talking about here is that, well, wait, if I'm talking about 4 or 5 time constants, I'm talking about something that's going to be well over an hour for this inductor to charge up or discharge, which doesn't make sense to us. We know that inductors and capacitors charge up relatively quickly. And 60 microseconds, of course, is quick. If I did even 5 time constants, that would get me to 300 microseconds, or 0.3 milliseconds. So that does charge up or discharge really fast. In this case, it's discharging. And so we know that this doesn't necessarily really make sense. So because that doesn't make sense, I know that this is the wrong way to do it. Okay, so I have my tau now. I just need to figure out what my initial current is. Well, what's the other piece of information we've been given in this problem? We've been given that the initial energy is 0.960. Now remember, our formula for the energy inside an inductor is 1/2 L I squared. But if this is the initial energy, so I'll write this as W, or omega sub 0, that's equal to 1/2 L, and then this would be I sub 0 squared. It'd be my initial current. And so all I have to do simply here is plug in here 0.960 is 1/2 times 0.12, or I'll go ahead and write it as 120 millihenries, times my initial current squared. And then we just have to solve that. Now you can solve it however you want to. I'll write down the formula that would give you the computation for the solution. So this would be 2 times 0.960 divided by 120 millihenries, and then the square root of that, which gets you 4 amps. So now we're ready to write my answer down. There's not much else I need to do. I can write then that the current through this is, well, my initial current is 4 amps, e to the minus t over Now if I'm going to write this as tau, I need to make sure to put that this is microseconds because I need to make sure that when I'm plugging in, or there's another way to do it here. I'll show you another way to do it here. So negative t over 60 microseconds amps. So this is how we'd want to write it, or another way to write this is to, instead of putting the unit there of 60 microseconds, you can say 4e to the negative t over 60, where t is in 60 microseconds. I guess there's a third way to do it. I personally don't care for this method, so I'm going to write it in red. I don't like doing it this way, where if you just simply do 1 over 60 microseconds, you would get 4e to the 16,667t. And I don't like writing it this way because this number, 16,667, has lost all meaning to me. It's a number, I multiply it by t, but it's lost all meaning, where when I write it in the time constant form like I have here, that time constant form means something to me. Oh, 60 microseconds, I know 4 or 5 of those, the inductor is going to be discharged in this case. All right, so let's move on to another example here. Now this example here has got a switch in it. So let's write down what it is we're asked to find here. So first off, the switch, let's write the information that we have here. The switch has been closed for a long time. At t equals 0, the switch opens. And we'll divide this up into parts here. Our ultimate goal is just to find that current I. What we're going to do here is we're going to first find my initial current, then we're going to find my time constant, and then we'll wrap up with finding I at t. Now, when it says the switch has been closed for a long time, let's first just modify the circuit diagram. So the switch is closed. Now, why does it say for a long time? Remember, a long time, we use that expression to indicate that capacitors or inductors are fully charged. So that means this inductor is fully charged, and we know when an inductor is fully charged, it actually behaves as a short. Now what that means currently, I'll go ahead and erase this 8 millihenry here because it's now a short here, but that also means that this 2 ohm resistor is not there because I've shorted it out. Current's always going to take the path of least resistance, and a wire has 0 resistance, so that 2 ohm resistor essentially disappears here. Now what do I need to do? I need to find the current going down through here. I want to find this current. Now there's lots of ways to find this current. One is to do a loop analysis, which you could do, and you could do a loop analysis by doing, I1 here, and then I2, and I'll emphasize here that I2 would be that initial current, because that's the current going through the inductor, because the inductor is now like a short. I'm actually going to do something a little bit different, and I'll see if you guys can figure out why I'm doing this. I'm actually going to do nodal analysis, because I've got a single node here and a node here, but this node is all the same node as up here. And so this node I'm just going to put to ground, and that means this is 120 volts here. And I'll just label this as VA. And so I'm going to find VA. So I have VA minus 120 over 3 plus VA over 30 plus VA over 6. And that's equal to 0. And then what we're going to do is, of course, multiply this by 30 to clear out everything. So if I do 30 divided by 3, I get 10. And so I'd have 10 VA minus 1200. And of course I get plus VA, and then 30 divided by 6 is 5, so plus 5 VA. And so you get 16 VA is equal to 1200. And what we wind up getting for VA is that it's 75 volts. Now, some of you might be saying, well, why did I bother finding VA? I'm trying to find this current I. Yeah, we are trying to find that current I, but I'm thinking, oh wait, if I trace that current back, this current I, that current, if I kind of trace back what it's doing, it's the current flowing through that 6 ohm resistor. So I know here that my initial current here then is just the current through the 6 ohm resistor. Well, there's 75 volts here. There's 0 volts down here over 6 ohms. So you get 75 divided by 6, and you get 12.5 amps. So this is my initial current. Okay, now it's asked to find tau. This is after the switch has opened. So when it's asking you to find tau, we're always referring to the switch being opened or closed. Now, if I open the switch, I now have the following circuit. Two ohms and 8 millihenries. Because I've opened it, I've disconnected that inductor from the circuit, and it's now attached to this 2 ohm resistor. And you might say, well, wait, the inductor is behaving as a short. No, that's when it's fully charged. As soon as I open it, that inductor is going to start discharging. It's going to start giving energy to that 2 ohm resistor. And so, well, here, this is just like the very first example we did. So the tau here would just be 8 millihenries divided by 2 ohms, which would be 4 milliseconds. And so part C now is easy. I at T is just my initial current, which is 12.5 amps, E to the minus T, and I'm just going to write it as minus T over 4. This is in amps, and I'll say where T is in milliseconds. So that's important that, again, we indicate that it's in milliseconds. Let's add a fourth here. Approximately how long does it take for the inductor to discharge? And that's an easy question too. We actually can answer that question without even having part C done. Remember, that's where we say 4 or 5 time constants. I like to use 5 tau to discharge or charge, because we're going to talk about charging up capacitors next and inductors. So it's 5 tau to charge or discharge. Well, that would just be 5 times 4 milliseconds, which is 20 milliseconds. So that's how long it's going to take for us to charge or discharge. And these kinds of computations are important here, and I'm going to have to end the video here. I don't want to take too long. We will go through an RC example in the next video, but let me give you an example on why this is important here. Suppose we're using an inductor here, and we're using this as a choke. So basically what we're using this as is that, you know, the circuit's been on for a long time, and I'll just say, you know, here this is power grid. circuit's been on for a long time, and so then it's going to act as a short, but then suddenly we get a spike on the power grid. Well, this isn't going to act as a short. It's going to, if we get a spike of power, like a spike of current on the power grid, it's going to take time for this inductor to charge up to respond to that spike of current. And as long as we size it correctly based off of what the loads are here, computing the time constant correctly, if the spike only lasts, let's say a microsecond is how long the current spike lasts, well then having a time constant of 4 milliseconds is going to be plenty to choke out that spike of current so that it doesn't get into our circuitry where this load is basically household circuitry or whatever. So that's why some of these time constants are important, is that's how we can size inductors if we're using them as current protection devices in circuits. You can use them to size it like that. Now of course the larger the inductor, the longer it's going to take to charge or discharge, but you don't necessarily want to say, oh, well, I'll just put a huge inductor in there because, well, there are other issues with inductors as they create magnetic fields when you run a current through them, especially if it's an AC current, and that can cause some issues as well. Or another reason is they tend to be expensive. So you also want to make sure that you don't just spend money frivolously. All right, so let's end this video here, and then we'll do an example with a capacitor.